Okay, so good morning once again. I want to look at wavelets. So far, I've been dealing with, I'll say, two main types of wavelets, bivariate and multivariate. And they fall in the category of time frequency domain or time and frequency domain or frequency domain. We'll explain what that means. I think we explained that some time ago, but I usually start with this diagram. So if you look at this plot, this is a time series of some stock markets. Okay, just take one of them. Is this representing short term, long term, or medium term? That's the question. So you may say this is short term or long term, but usually you say long term. The question is, even if you take time horizon, which is short, medium, long, or those ones in between, usually anything more than 1 year is considered long term. Accountants do that, economists do that, finance people will also do that. In fact, for finance, 1 year is too long for a long term. But let's take it like from 1 year is long term. But this data is between 2017 and 2011. So that's very long. That's how many years? 6 years. So it means that maybe all of the data is in long term. But the answer is that this data is only a long series. It doesn't tell us long term, short term, or medium term. Because once you move out of 2011, for example, everything else is long term. If you are going according to the definition of 1 year being the beginning of long term. So obviously, this has long term, but that's not the only thing it has. It has short term, medium term, and all the intermediate ones. If there's a way to break this long data down into the short-term components and medium-term components and long-term components, that would be a good idea. So that when you're analyzing your data for whatever purpose, you analyze them based on these time frames or time scales, which you also call time horizons, which we also call intrinsic time. But you see, the 2011 to 2017 is your calendar time. And then your intrinsic time is short, medium, long term. That's important because in whatever market that you operate in, market participants are decision makers who take decisions according to time horizons. We have short-term decision makers, long-term, medium-term. They are there. Now, whatever variable you are dealing with, the data that you have was generated based on these market activities. So the data generating process is based on short-term, medium-term, long-term decision making, which has generated this data. Which means if you take even 1 year, in the 1 year span of data, there's the short-term component in it, long-term and medium-term. That means for the whole length of this data, you have short-term, medium-term running through. Okay. And you want to be able to deal with those ones, what we call decompose the data into those components. Then you can talk to the data in that sense. So far, what we have been dealing with is time domain analysis, or the regressions, or the gauge is just time domain. In fact, based on how we did a lot of it, we did time varying. So it changes from one period to the other. This time you want to have the time component, which is your calendar time, 2017 to between 2017 and 2011. And you also want to have your time frequency or your time horizon, which is short term, medium term. So that makes your data rich, because at one point you're only talking about calendar time. Now you can talk about calendar time and the time horizons. So you have moved from time domain to now time frequency domain. That makes your data richer. So you have more insight into your data for analysis. In another sense, you can also strip the data of the time series aspect and only deal with the time horizons. So that will become frequency domain. This particular one that we are dealing with is going to be both time and frequency domain. Later, we'll deal with only the frequency domain. So this is the background to what decompositions are about. So depending on which decomposition you are looking at, some will only give you frequency domain, some will give you time and frequency domain. And you need to know the research question you're asking to choose which one of them. For example, when you want to look at time horizon analysis vis-a-vis lead lag relationship, you have to do with a time frequency domain approach. So there's a question here I want you to look at. If you have time domain analysis, your question that you can ask is when, in terms of calendar time. Frequency domain is also when, in terms of how long, which investment horizon that you are dealing with. So when you combine time frequency, then you can ask when and how long. So when in terms of calendar time and within what time horizon. So that is two. And when that happens, you have to deal with some magnitude, direction, and of course, association for between one or more variables. Okay. Now, this area of research is new because economists knew that there's a relationship between some macroeconomic variables and time, as well as investment horizon, which is frequency domain. But they didn't have the tools to extract those components to deal with until computational power became common and statistical tools became common. Those in the early years who did some economics and statistics, if they tell you how the stress that they go through in order to make an estimation, there's one computer sitting in the department where you go and the computer has some punching holes. So if you have to calculate, you have to punch some holes in some papers, you cannot do this if you are dealing with high frequency data, daily data, spanning several years. So economists knew this was there, but they had to wait until the tools were available. And these are the tools that we have available now that we can use. So this is a code from Ramsey and Lampert 97, saying that economists have long known time scale matters. So this is the frequency domain. In that, structure of decisions as to the relevant time horizon, degree of time aggregation, strength of relationship, and even the relevant variables differ by time scale. So you see when and how long in terms of investment horizon and the strength, the direction of association, they matter. Okay. Unfortunately, until recently, it was difficult to decompose economic time series into orthogonal time scales. Orthogonal just means opposite. So we'll see the opposite very soon. Okay. Orthogonal time scale component, except for the short and long run, in which the former is dominated by noise. That's very important. The former is the short term, which is dominated by noise. We'll talk about that also. So looking at this idea of degree of time, aggregation, strength, one of the tools that is very useful is the wavelet approach. And the specific one that we are going to use is the one that can give us the degree, the magnitude, the aggregation, and especially the lead lag relationship, which in some context is causality relationship. Okay. So the versatility and attractiveness of the wavelet approach lies in its decomposition properties, its time scale localization. It is especially relevant in analysis of non-stationary time series, i.e. short-lived transient components. So transient means doesn't last long. And that's important because we'll see very soon that the name wavelet is very important. Fortunately for you, everybody has seen the Gulf of Guinea, the ocean. You see the sea waves. It's the same idea from there, because the waves will start from a particular place and they will end at a particular place. So short forms of waves is wavelets, like that. And how is this relevant? Because in economic and financial markets, situations arise and then they die off. There may be some volatilities that do not last long. There may be some news item. There may be some spares of disturbance in the market. So if you have a long series, you want to be able to isolate those events. And that's why these tools are important. Okay. So how do we do that? We do that by taking the data and breaking the data down, what you call decomposition. And in this particular instance, we want to break the data down into the short, long, and medium terms. Now, the data that you have, whatever data you have, we call it signal. Also, remember, as we saw earlier, that these tools were not available until recently. These tools are physics, statistical, mathematical, engineering tools. So that's why they use those terms, signal. So the data that you have is your signal, like your typical stock market data. And that data has noise in it, especially in the short term. And we know what noise means. Any data component that deviates from the fundamental relationship. Okay. Panics in the market that is causing trading activity that are not the fundamental, like what behavior economics of finance talk about. So we want to be able to decompose the signal into noise and the signal itself. So noise signal ratio, that's what we are looking at. So one good idea about these decomposition tools is that in the process of decomposing the data into short and long term and medium term, they also try to reduce the noise in the data so that the signal noise ratio, so to bring it down as much as possible. So if you look at this, so there's a signal. Okay, so we have a signal, random signal xt, and because it's a time series, it's going to have this time component. And as any series, it has its residual parts, and t is calendar time typically. So what you can do is to do two things. Transform the data into frequency domain. So you just delete the time components. So you realize here that the time lag, the time stamp is gone. So we decompose into what we call the W, and then each one will have WI. So we don't have T again, and I is 1, 2, 3, 4, which we call time scales. We'll come back to them. And they are also called frequencies. So here you realize that the time is gone, only the frequencies remain. So what you realize is that at the time series, we can ask the question as to when, calendar time. At the frequency domain, we can ask the question as to at what in the investment horizon. So this lacks, the time component lacks the frequency aspect. The frequency aspect also lacks the time component. We want to have more insight into the data. You want to be able to deal with the two. And that is the time frequency domain, which generally is referred to as spectral representation. So spectra in space or spectrum, we'll look at that as well. So how do we do that? This is general in general terms. Okay, so you choose a window. By now, I think we know what windows are. Then you choose a localization, which is around an origin. We'll come back to what localization means. And then the signal is X, and we choose an instance where we are going to start shifting the window from. Okay, so to do that, you are going to have a product of the signal and the time, and then the instance where you are going to shift. And you multiply that by the signal X, that's going to give you a time frequency domain. So this is general representation. When you go into the specific decomposition, I'll ask you where we can see this representation in that method. Okay, so this, when we do this, then we can answer the question of when and how long. Okay, so we move on. So the specific tool that we are going to use is the wavelets. So let's talk about it a little bit. So wavelets are, as the name suggests, mini waves. And they begin from somewhere and they die off. So they are localized. That's the idea of what localization is. In statistics and mathematics, we have global and local. global and local solutions, right? So local is restricted within. So we saw that we have this 60-year data set. So if you calculate correlation or mean for the whole period, that would be a global mean. But if you split the data into the portions, each of the means that we have will be a local mean. Okay, so that's the idea. So local rather than global. And they have defined number of oscillations. Of course, if they are going to begin from somewhere and end at some point, you can always find how many oscillations that they have. And we are also saying that it is reasonable to examine periodicity. Periodicity is the frequencies in time series, and which is the potential of changes over time. Okay. Now, earlier we mentioned that this is a spectral representation. Spectral is representation space and time. So an object that is in motion over a period of time, how are you able to pinpoint the exact location of that object? So that is what we call the Heisenberg uncertainty principle. The uncertainty principle is that you cannot have a precise measurement for something that has velocity and position at the same time. And if you look at it carefully, there's a mathematical representation of that. What is that? If you have a plane and you have some direction and you also have some magnitude, it is called what? It's called a vector. Vector is any object that has magnitude and direction. So as you go along, realize you'll be dealing with vectors. Okay. And this is common again, realize that this is not finance. This is engineering. So signal processing, image processing, medicine, astronomy, biology, climatology. Of course, if you are talking about waves, that's where it's coming from anyway. So when you have our plane, we should be able to see that there's some direction as well as magnitude. So it has become common in finance and economics. We mentioned that because now the tools are available, and especially the tools are also free. Okay, so we can use them to do deeper analysis to know cyclical patterns that are otherwise hidden. And we can transpose or transition what correlation is into this framework. So we can be talking about correlation, which most economic and finance studies are about, all about relationships, your macroeconomic variables, your stock market variables, your financial inclusion, all these variables are about correlations, in other words, relationships. So we can study those relationships at this level, and those will be deeper, and we call them coherence. And in some sense, if you are looking at relationships, you can extend them to levels where they are integrated, like your co-integration. And if you are talking about more variables, you can also look at how they converge into some standard. For example, when you have economic blocks like the West African Monetary Unit, ECOWAS, all those ones, for them to fully operate, they need convergence criteria. They need to meet convergence criteria. What is the inflation level that everybody has to achieve? What is the exchange rate level? What is CPI level? All those ones, you can take them with some of these things, especially because we have short-term, long-term, medium-term. So convergence as well. We also talked about lead lag, which if you are in a system of economies of variables, which variables are the dominant ones and which ones are the followers. So the leaders and the followers is always good to know that you can make decisions. And they are also can be inferred for causality. So why are we using wavelets? And especially this particular wavelet, we talked about the localization aspect. So we decompose them so that we can talk about the relationship in a particular period and frequency. It can help us to look at the fluctuations. And the two things that are also important is stationarity and, so stationarity. So your typical time series data, you want it to be stationary before you analyze. And that's because your analysis is on a global level. That's why you want stationarity. What do we mean by stationarity? The statistical properties of the data is constant over the period of time. We are not interested in over the period of time. We are decomposing according to short patterns. So we don't need stationarity. So we can forget about stationarity because we are doing what we are going to have is local stationarity. And you are likely to get local stationarity because if the data is short, the statistical properties are very likely to be the same for that period. You can also infer normality as well. If the data is short and it's large enough, let's say 40 data points, and it's within a short period, then you can also assume normality. Okay. So when you are dealing with this, you don't need to worry about this stationarity and normality assumptions. That means that we are moving into non-parametric frame of analysis. So it's distribution free. So then that means you are doing non-parametric. Okay. But that's general. So if you want to compare it with other forms of decomposition, so this one we are doing wavelets, other forms of decomposition. Most, in fact, all decompositions are based on the Fourier transform. Remember, we say we are going to transform the data. Fourier transform is one of the best transformation techniques that are there. Compared to wavelets, it has some weaknesses. So the Fourier transform does not assume stationarity, which we are saying the wavelet does. So that's an advantage. It has the wavelet has finite energy. So it starts from somewhere and then it dies off. The Fourier transform doesn't have that. The wavelet can also, earlier we said we want to reduce the signal noise ratio. The wavelet can reduce the noise in the data set. So it's a denoising technique. There are specific tools that deal with denoising, but most of the wavelet techniques are also able to reduce the noise in the data set. That the Fourier transform doesn't do that. Okay, and the Fourier transform is a typical frequency domain analysis. It doesn't have time domain. So the Fourier transform will just forget about the time and stay with the frequency, but this wavelet will take the two. Another common filter is the Kalman filter, which maybe another time we can talk about. So based on these properties, we can employ them in dealing with investment horizons and business cycles. Theoretically, which tools do you think this one appeals to? We talked about the behavioral finance approach, where investors behave based on different dynamics. One of the theories that is common is the adaptive market hypothesis. Adaptive market hypothesis. So investors adapt the market dynamics. So in this time and frequency domain, the time aspect will speak to the adaptive nature of investors. So from this, let's say first July to 20th July, if the market changes, following the next day, they will also change their patterns. They are rational beings. Okay, so they will change. Even though the behavioral aspect will think that we are usually irrational, but there are some aspects of rationality which will cause the investors to change. Even if the change is irrational, like panic and herding behavior, it's still a change. So we want to capture that. Then there's another theory called fractal market analysis, which is also in agreement with what we call the heterogeneous market hypothesis. So the heterogeneous market hypothesis is based on the fractal market analysis. Where are the fractals? What are the heterogeneities coming from? That is the idea that investors are different in terms of their decision making according to time horizon. So you typically have short-term investors, long-term investors, medium-term investors. And these are very practical. Okay. You realize that investors that are in the short term are risk takers, and they are those who speculate on the markets. So when you have investors or market participants, we have those who want to beat the market and those who want to match the market. So those who want to beat the market are usually short-term participants, they are risk takers, they will speculate on the market. The other side will be hedgers, they will just protect their positions and they will bet with the market. Okay. So you're able to now look at your analysis in terms of different market participants. That's the heterogeneous market hypothesis. Okay. And the Wavelet is able to help us do that. For that reason, it is becoming more and more difficult, if you look at the literature, that most of the studies are in one way or the other decomposing the data into some time and frequency domains in their work. If you look at the finance and economic literature, that's what is available. So if you don't have a very strong story to tell, then you may have to spice that up with a strong methodology, which are some of these. Okay. So far, we have talked about other transformation tools or decomposition tools. A few of them are listed here. We said wavelets can denoise, but that's not their main tool. But we have tools that are purely denoising tools that are also purely frequency domain tools. Even later, we'll look at wavelets that are only time domain, no, frequency domain. Okay. So if you look at the EMD, which is empirical mode decomposition tools, they are purely denoising tools, which will now give you frequency and domain without time. Okay. We also have the variational mode decomposition. That's also another decomposition tool. Okay. So if you have any decomposition tool that also reduce noise, that's more desirable. Okay. Now, let's look at the wavelet itself that you want to deal with. Wavelet has two components, and as the names suggest, as funny as they are, we have the mother wavelet and you have the father wavelet. The mother wavelet, if you look at it carefully, see it integrates to 0 and the father wavelet integrates to 1. And look at it, there's this low frequency, smooth part is also the trend. Then the mother wavelet is high frequency and it has deviations from the trend. The question will be, between the mother wavelet and the father wavelet, which one do you think is closely related to the short term? Which one is closely related to the long term? It's clear that the mother wavelet will be the one that's close to the short term all the way to medium, because the trend is always the long term. What is the trend? The long-term behavior. So when you are decomposing, mainly you'll be decomposing the mother wavelet. And the smooth part will be the father wavelet, which will be for long term. So this general representation. Now, you see the integration sign here as we go along. I think I prefer to use summation sign, and we know summation sign and integration are synonymous. So which wavelet are we dealing with? A particular one that we call the complex valued wavelet. Complex valued wavelet. And in fact, the specific one is called the Morlet wavelet. Why do we want to deal with the Morlet wavelet? And why do you want to deal with a complex valued wavelet? Because if you want to look at a spectral analysis, which means you have a vector that is in space, that can also give you amplitude. Amplitude is basically magnitude. That can also give you direction. You should be in space. You should have a vector. So you should have a complex valued item or variable. One complex valued wavelet is the Morlet wavelet. Okay. And if you have a complex valued number, we know complex number is like if you have X, a little trip to mathematics. So X is going to be I plus Xi plus Y. So we have the I is the complex part and Y is the real part. So if you want to deal with any relationship that has amplitude, which is magnitude and direction, then we have to choose a complex valued wavelet. If you have a complex valued wavelets and you decompose, you are also going to have complex decomposition. Okay, and we are going to use those to see our direction and magnitude. Okay. So another thing is that we want it to be continuous because given the data that you are dealing with, a continuous wavelet will be better. And they should also be orthogonal. Orthogonal means they are opposites. So for example, the conjugate of a number is its opposite. And we can only get a relationship if we have a conjugate and we take the fraction of that, that will give us an angle. We'll look at that a little bit. That's a little bit of mathematics, but we have to deal with them because we are stealing from them. Okay. So all these properties are in the continuous Morlet wavelet, and that's the one we want to use. Okay. One thing here is the fact that it is not restricted by downsampling. Downsampling is an idea where you have a wavelet and you are decomposing. The scales that you are decomposing should be a whole number. So if you have a discrete wavelet, so if there's a continuous, there's also a discrete. If you have a discrete wavelet, we need to have a whole number as the number of scales. So if it's not whole number, then you need to adjust the data set to get the whole number. And that you can do that by downsampling. So basically reducing the data set. But the question, why not upsampling? Because you cannot just go and generate new data and add, but you can remove some of the data. So that's why continuous wavelet is important. We'll see very shortly how that plays out. And we have a term for it, we call it dyadic wavelets. Okay, so let's look at it. We can deal with this also in terms of univariate or multivariate or bivariate. So you can have a single data set, you decompose it into short and long-term dynamics, and you analyze them, or you can have two or more. Okay. So I have explained that if you want to look at amplitude and direction, then we need the complex valued wavelet. So I think I need to put this thing here now. So you can have your real here, and then you can have the imaginary here. Okay. So you can have a vector Z, which has an imaginary part and a real part. Okay. So imaginary is the one with the I, and real is the one without I. Okay. So if you use this, X can be the real, and Y can be the imaginary because it's the one that with the I. Okay. So you can have an origin here. Maybe that wavelet is like that. Okay. So that is a vector because it has both the imaginary and the real. There's the conjugate. The conjugate is the opposite. So if you make this, let's say, X minus IY, that's the conjugate. And that can be, so negative will be this side, right? So that can be a conjugate. So we have your real, you have your imaginary like that. And we are going to find the angles between them. The angles are going to give us the lead lags, and then we are going to transform the angles into frequencies, which you will see very soon. Okay. So that's how the complex valued wavelet look like, the Morlet. Okay. The implementation of that, we are going to follow the process by Roche and Schmidt-Bauer, and they did that in the wavelet comp package, which has a very detailed description. So look at this representation here. This representation, we have an object phi t, so that's a time series with a pi. So pi has to do with angles. Already we saw the complex conjugate has angles that we have to deal with. And this is the complex part that we have to look at, the IWT. So that's the complex part. And E is our Euler's E, which has several mathematical properties. So what are they? What do they represent? So omega is rotation in radians per unit. So that's angular frequency. We are going to transform that into frequency domain. Okay. Says that W omega equals 6. That's an analytical solution. So that gives us desirable properties. So 2 pi is 1 revolution. the inverse of that is basically 1. So you see why we chose radians of 6. So 2 pi by 6 is approximately 1. So that's why, to get 1 revolution. Okay. Then this is the representation. That's how they look like. So this is a typical modern wavelet transform. And the real part is the black line and the imaginary part is the green line. So we should always see the two. In fact, when we do ours, we'll see. I think it will be in red and black. Okay. And this is how the magnitudes look like. They are sine and cosine representations. I mean, you don't have to worry yourselves with that, but that's how they will look like. But this is a mathematical representation. So all of this is univariate. We can get into the multivariate very soon. So the idea of spectral analysis, you have an origin, you have a window, you have a time space that you have to shift across and multiply by the signal, which I showed in the earlier slide, is here. So this is the way you see, instead of integration, we are using sigma. So this is the signal. We have the shifting that we talked about. It was t minus g minus t. This is t minus tau, and tau is important. And the phi star is the real imaginary valued object that we saw in the previous slide. So this whole phi star is the Morlet representation we saw earlier. Okay. And then we have to choose an S, which is our scale. Tau is our localization, and star, which is the complex conjugate we saw earlier. So what we are going to do is that we are going to shift, because this is, see dt is an integration. So that you can refer to this part as the dt. And S determines the wavelet coverage, which will be number of scales. We'll talk about that later. Now, one idea with the scales is what we call an octave. So octave is usually, oct is 8, right? Or 6? Oct is 8. Okay, so in music, we even have octave and those things. But here, in this particular sense, we are saying it's a fractional power of 2. So we are going to have 1 over 2 power j, which means we have the wavelet decomposition are going to be 2 to power j. So if you have 10 scales, you are going to have 1 all the way to 10, and each one is going to be 2 power 1, that's 2, 2 power 2, 4, like that. Okay. So that's how it looks like. A frequency that is 2 times higher. Okay. So bear that in mind. We'll come back to it. And you have to understand this is overly simplified relationship. Okay. So we talked about we don't need to stress about this. So this is trying to deal with how the octave behaves. Like now, we talked about the angular frequency, which was 2 pi over 6, and we can always take the inverse of that. So minimum or maximum scales is fixed via the choice of minimum or maximum period through this conversion factor, pi over 6 or 6 over 2 pi. And this will change the angular frequency into frequencies. Okay, so you see that 1 over s here is a representation of that 1 over 6 over 2 pi and 2 pi over 6. Okay. So how do we select the scales? We talked about that. The scale should be a maximum of n is the number of data points. So n is the number of data points. The scales that you choose should be at most n power 2 power j. So 2 power j is, if you have 5 scales, then the last power will be what? 2 power 5 is what? 32. So your data set should be at least 32. That's what it means. Otherwise, you will have a problem. Okay. Generally, how do you choose j? It's log base 2 of n. So if you have any data points, and you want to know how many scales is going to fit, theoretically, it should be 2 log 2 of n. So you have 100 data points. The number of scales you should choose is log 2 of 100. Remember, that's the theoretical J. In the empirical estimation, the J that you choose theoretical may be too high. But in practical sense, how do you choose a J? Remember, you are making an analysis over frequency domain. So short-term, long-term, medium. Yeah. How many time horizons do you want to deal with in your analysis? So if you are doing a typical economic analysis, let's say purely macroeconomic, you are dealing with maybe yearly data or quarterly data. And if you are dealing with, say, business cycles, a business cycle is purely, one cycle is 10 years, right? One cycle is 10 years. So even if you choose an J of 3, that's already one cycle. And one cycle, 10 years is a long, which means if you choose 3 skills, then you can talk about short-term, long-term, medium-term with 3 skills. But if you are dealing with, say, daily data in a typical financial market and you choose 3 skills, remember, 2 power j, so each of the 2 power j will translate to the length of the frequency you are using. So 2 power j, 9 years, that's like a decade. 2 power j of daily data, that's 8. 8 is 2 weeks for daily data. 2 weeks for daily data is at best you are just exiting the short-term frame, which means medium term is basically gone, and then long term is also gone. So you can't talk about the long term, you can't talk about the medium term. So you may want to choose more. Maybe you choose 10. 10 is what? 2 power 10 is what? 1064. 2 power 10. 1024. Daily data. Remember, 1024. Remember, in a typical stock market data, 1 year is 240 days, 245 days. Take holidays, take weekends out, 240 days. Times how many? About 3 will give you 1,000, thereabouts. Or less 2. 2 will give you 1,000. Now, that is a long, you're already inside long term. So imagine you go in and choose skill of, say, 12 or 15. You are in daily market framework. Who cares about 5 years from this market? Nobody cares. People care about maybe at most a year and beyond, not 5 years, not 3 years. So this is how you choose your skill. You have to have a motivation for the skills that you choose. Especially in this particular wavelet, the skill is chosen, you can choose it arbitrarily. And then that has to be justified. In some context, the data will choose the skills for you based on what is happening. So choosing the skill is important. Okay. And the wavelet skill should be dyadic. In other words, it should be divisible by 2 power j. So this is what it means. So divisible by 2 power j. So n 2 power j. Mainly for discrete. If it's not, then you have to downsample. Of course, dyadic means different things, different contexts. In this particular context, it should be divisible by 2 power j. If it's a discrete wavelet, this has to be strictly adhered to. For continuous, you don't need this because continuous doesn't have to be divisible. So let's go into a little bit of what the decompositions can give you. Composition can give you. Okay. So you are going to have a power spectrum. Remember, we are doing spectral analysis, so you are going to have a spectrum. Okay. The spectrum is basically amplitude. Amplitude is basically magnitude. Okay. So there was a scale earlier that we saw. So this is root of S and the decomposition of the scale over the tau. And it's a magnitude. That's why I have the absolute sign around them. Okay. If you square that magnitude, you get power. So you can convert the spectrum to power, which is easier to deal with because you are in time of frequency analysis. Okay. So this is just square of the first one. And this is straightforward. Okay. And what does that mean? That represents variance. And this variance is not global variance, it's local variance. Okay. And what does it tell you? It tells you of volatility within that localization. And remember, all of this is univariate decomposition or univariate wavelets. So where in the data, according to time and frequency, is a lot of volatility at. You can do that with the power. Okay, then let's move on to something else. So we talked about what the power represents. And remember, we have already established that this is non-parametric analysis. So our results are going to be mainly graphs, and particular one will be heat maps, which we'll see very soon.